Well, thank you very much. Thanks for that generous introduction. It's really a pleasure to be here and to be back at the Max Planck Institute after not being here for a long time. And I just have to say, you know, the whole notion of being a hero makes me a little uncomfortable and unhappy. I think of myself as a scholar, an intellectual, maybe a public intellectual. And so what I want to do today is to talk to you a little bit about my journey and how I ended up in this position that you or someone else might call me a hero. And I will tell you one funny story. About 15 years ago, I was invited to lecture at Brigham Young University. How many people here know what that is? A few, oh, quite a few, okay. So it's a Mormon university. And when we arrived there, I was hosted by a woman postdoc who ran up to me, threw her arms around me and said, "Mom," and said, "Naomi, you're my hero." And I had brought my daughters with me, and my older daughter was about 15 at the time. She goes, "Mom, you're someone's hero? And a Mormon?" So we can end up being heroes in ways that we never expected. And my story today is really about that. I didn't plan any of this, but it happened. So in a way, my story begins in 2004, when I published a paper in Science magazine documenting the scientific consensus on climate change. The paper reflected my long-standing interest in scientific consensus, and particularly the question of how scientists decide when we have enough information to say that something is known scientifically, or in plain English, to say that something is true. This was the subject of my first book, The Rejection of Continental Drift, which I'm going to make a shameless plug for because, like all mothers, my first book is my favorite, you know, firstborn child and all that. No, don't tell my children I said that. But because in a way, I do think that in this book, I laid out what was and has been my intellectual agenda really throughout my whole career. So in 2004, so that book was published in 1999, and in 2004 I was invited to give the George Sarton Memorial Lecture at the American Association for the Advancement of Science. So there's a big deal lecture. We had about, I don't know, 600 or 700 people in the audience. It was probably the first really big public lecture that I ever gave. And so I decided to talk about this central question that I had raised in my book, consensus in science, how do we know we're not wrong? Scientists agree on something, they say, yes, here it is, but what is our basis for understanding the meaning of scientific consensus? And so I framed my lecture starting from what philosophers of science have called the pessimistic meta-induction. That is to say, we know from history that many, maybe you could even argue most, past scientific theories have eventually been overturned. They've been adjusted, modified, or even in some cases rejected entirely. And this suggests that our current scientific knowledge will in time be overturned as well. So on what basis can we say that our current scientific theories are true? What basis do we even have to accept the findings of science at all if we know that there's a good chance that in the future they'll be overturned? And what does this tell us about the character of scientific knowledge? How should we think about scientific knowledge, knowing that it's fallible, perishable, and in some cases just plain wrong? So in my lecture, I focused on a set of well-known historical examples. The most famous of one, of course, which many of you will be familiar with, is the example of the Ptolemaic system of astronomy. It's very well studied. There are lots and lots of books and academic articles that have been written on it. We know that for a long time, people used the Ptolemaic system to make predictions of the planets and eclipses. Those predictions were accurate. The Ptolemaic system worked. And yet today, we would say it was wrong, that we all know that the Earth is not the center of the universe. So I talked a bit about that. I talked about some other examples, and then I talked about my own work on the theory of continental drift. So as many of you probably know, there was a big debate in the 1920s and early 1930s about this idea that continents moved. It was resoundingly rejected in the United States. In Europe, people were a bit more open-minded about it. But in general, scientists came to the conclusion that it wasn't right, it wasn't true. But in the 1960s, the debate was reopened, and the basic idea, horizontal movements of continents, was accepted as factually correct. In fact, in the 1960s, a consensus emerged that the idea of horizontal crustal motions became a central premise of what is now and has been since then the dominant organizing theory of modern earth science, which is plate tectonic theory. So this raised the question that I posed in my first book. If continents really do move, as all Earth scientists would tell you they do, then why was this theory rejected when it was first proposed in the 1920s? Now, an obvious answer to this could be, well, maybe there just wasn't enough evidence, or the evidence wasn't sufficient. I mean, that would be an obvious, good philosophical answer, but it's wrong. In fact, there was a huge body of scientific evidence that was widely discussed by Earth scientists in the late 19th and early 20th century. This is from an illustration by the South African geologist Alexander Du Toit, who in 1927 published a book called Our Wandering Continents, in which he summarized the extensive stratigraphic, structural, and paleontological evidence that the continents had moved and some parts of them had been previously connected. These data were drawn from well-established scientific traditions in stratigraphy, paleontology, structural geology, and paleoclimatology. They had been collected by well-respected prominent scientists over several decades, and they came from all over the globe. So this illustration is specifically about South Africa and South America, but there was data from Australia, from Indonesia, from the United States, from Europe, pretty much, well, everywhere except Antarctica. In fact, I think we could say that what William Whewell called a consilience of evidence. There was a lot of different evidence, and it all seemed to converge on this single story of moving continents. In fact, one of the interesting things from the debate in the 1920s was that Alfred Wegener, who was the most prominent proponent of continental drift in the late 1910s and early 1920s, tried to demonstrate to his own colleagues that they actually had a consensus about this evidence. And so he put together this rather remarkable graph, really a little bit odd, but what he's showing here, so here's the geological time frame, so Cambrian, Silurian, Devonian, Carboniferous, Permian, etc. So this is geological time, so old here, recent there. And then these are the proposed connections between continents that would have been together in a former supercontinent, Pangaea or Gondwana. And so these are the four major links that were proposed: a Europe-North Africa connection, an Africa-Brazil connection, etc. And then he goes to the scientific literature, reading articles, and says, well, do scientists think there was a connection between Australia, India, Madagascar, and Africa in the Cambrian, Silurian, Devonian, Carboniferous, etc. And what he shows is there's almost unanimity among scientists that yes, there's a connection until the end of the Triassic period, and then something happens, and then it breaks apart and there's no connection. And the same with Africa and Brazil, Madagascar and India. And then Europe and North America is more complicated, which is maybe why the debate in the United States was more complicated. But overall, he's showing, look, guys, you have these data. You already have made the case for these continental connections. So all that matters now is to sort of put this together in a unifying theory. So one possibility, but we can now say it's not true, was that there just wasn't enough evidence. Another possibility, and this was widely claimed by scientists in the 1960s, was that continental drift was rejected for lack of a mechanism. That yes, scientists knew there was empirical evidence of these connections, but they didn't really have any mechanism that could explain how the continents could move. Well, that's false too. What I showed in my dissertation in my first book was that actually the exact same mechanism that was accepted in the 1960s to explain plate tectonics had been proposed and widely discussed in the 1920s as the cause of continental drift. In fact, the theory supporters considered that the British geologist Arthur Holmes had actually solved the mechanism question. Just one example of a discussion of this, Chester Longwell, who was a geology professor at Yale University, wrote to a colleague, "Holmes has a beautiful theory, and I believe it will be epoch-making." That was in 1926. So I won't go in today to why I do think scientists rejected continental drift. It's a more complicated story beyond the scope that we have time for here, but if you're interested, shameless plug, you can read the book. But my point of this was to say science is a learning process. And this means inevitably that the future will bring surprises. Now, sometimes this makes scientists uncomfortable. They get all nervous about this. But I think we should embrace this. I think we should say this is good. It's not something to be ashamed of that we've revised our thinking. It's something to be proud of, that we gain new evidence and new insights, and we revise our ideas in light of those new forms of data or insights or new methodologies. And this is what we conventionally call scientific progress. It's not something to be embarrassed about. It's something to understand. But it does imply, as many philosophers of science have on many occasions said, that we should sustain a healthy humility about even, or maybe even especially, our best scientific theories. We should not assume that simply because a theory is working well for now, that it will never change. So my work at that time and the argument of the Sarton lecture was really, to a large extent, aimed at scientists, because I wanted to counter what I saw as the epistemic arrogance of some leading scientists who were insisting on the absolute truth of scientific theories. And it seemed to me, and I think almost anybody in history or philosophy of science at that time would have said, I mean, this was just ridiculous. Scientists were saying things about science that were refuted by the evidence of history. And of course, this is still true today. Any of you in the United States who follow Neil deGrasse Tyson know that this problem has not gone away. Okay, so at the time I was particularly vexed by the physicist Steven Weinberg. How many of you know who he is? Not too many. Okay, well, some of the older people. So very famous Nobel Prize-winning physicist who had this giant fight with Stephen Shapin back in the late 90s, early 2000s. So Weinberg wrote a book with the title Facing Up, Science and Its Cultural Adversaries. And it was meant to be a defense of science as a source of truth. His title alluded to his view that science forces us to, quote, face up to unpleasant realities, that it gives us, quote, a cold view of the world with no hint of a divine plan or any special status for human beings. So it's a very anti-religious argument as well. But what I noticed reading this book was that it seemed to me Weinberg was also responding to developments in HPS and SSK, right? I said that, which suggested that scientific facts were not as cold and hard as he was insisting. And what struck me about this book was that Weinberg himself was strangely unwilling to face up to the cold realities of history. So he obviously is an educated, intelligent man. In fact, he's friends with Peter Galison, famous historian of science, my own thesis advisor. But when he addresses the historical observation that many past scientific consensus have not proved permanent, including in his own field, such as Newtonian mechanics or parity conservation, he acknowledges the fallibility of past scientific achievements, and particularly past scientists, but insists that many present scientific achievements are permanent. So in other words, rejecting the idea that history has anything to tell us about the present. Yes, things in the past were fallible, but not anymore. So responding to sociologists of scientists who had emphasized the social dimensions of scientific consensus, he wrote, quote, even though a scientific theory is in a sense a social consensus, it is unlike any other consensus in that it is permanent. Now, obviously no historian of science would agree with the claim that scientific achievements are permanent. And we would say there's no basis for saying that what we're doing today is radically different in this respect from what we've done in the past. So even though I'm a historian, it seemed to me important to address the presentist aspect of this argument, to counter what I call present-day exceptionalism. That is to say, to argue that we have no reason to exempt ourselves from the lessons of history, and to make a coherent argument for why we should accept scientific findings even while acknowledging fallibility. In other words, not to allow fallibilism to collapse into nihilism, corrosive skepticism, or quietism. In other words, to embrace what we know about the history of science, to acknowledge it, but not to make it feel like, therefore, we just throw up our hands and say, well, we don't know anything. So just to go into this a little bit more, it wasn't just Weinberg who was saying these things at the time. Many scientists were responding to lessons of history by invoking present-day exceptionalism, that the present was somehow an exception to these historical observations about the limits of knowledge. The claim was that, oh yes, well, mistakes were made in the past, but we've corrected them, and that's how we know they were mistakes. And we're more sophisticated now, we're more knowledgeable, we have better instruments, and especially in the 1990s, we have computers. I mean, this is when computer modeling was first starting to really be a big thing in science. Now, of course, none of these claims can really be tested, but we can provide evidence to problematize the assumptions behind it. But that can make it seem like we're rejecting science to core altogether. And I think that's what many scientists back in the 90s and 2000s reacted to. They didn't like the feeling that history and philosophy of science and sociology of science and SSK, by raising these questions about science, were somehow, it seemed to them, discrediting science. And so for me, part of the question became, how can we acknowledge these realities without it seeming like we're just trying to throw science in the, throw science away? So my project then, and in many ways still today, is to make a robust argument for the value of science without invoking absolutist notions of scientific truth that fail historical, philosophical, or sociological scrutiny. And this is a project that, in the face of climate denial and COVID-19 disinformation, I would argue is now more important than ever. So, this brings us to the obvious present-day example, which was then and still is today, climate change. So, in my talk at that time, and again, still speaking from the vantage point of 2004, nearly 20 years ago, I was particularly concerned with one aspect of climate science. And again, this question was coming up because there were lots of people at that time saying, well, okay, maybe climate scientists are saying all these things, but maybe they're wrong, and why should we spend a lot of money and inconvenience ourselves and give up flying or give up meat if we don't even know if the science is right anyway? So I wanted to take that critique seriously, and I was particularly concerned about the prominent role of and reliance on numerical simulation modeling in climate science. In 1994, I had written a paper that became widely cited cautioning against exaggerated epistemic claims for what people were calling validated models. I argued that many people were conflating validation with truth and that was problematic, and that models, like scientific theories in general, were best understood as representations, and that they were most useful when they were used as heuristic devices. So my colleagues and I wrote, the primary value of models is heuristic. Models are representations useful for guiding further study, but not susceptible to proof. So I had written this paper, it had got a lot of attention, it was widely cited, I received a lot of invitations to talk about models in science. And at the same time, climate science relied very heavily on models. I mean, it still does to some extent, particularly general circulation models of the Earth's climate system and integrated assessment models that tried to bring in the economic and social dimensions of climate change. So if models like these could not be proven to be correct, then how could we justify relying on them to make major consequential policy decisions? And particularly if we knew from history that models could be quite wrong, and on some level that all models are wrong on some level. So this question about the role of models connected climate change, our present day issue, with the work I had already done on continental drift. And here I am now going to return to this question of why scientists rejected continental drift, if it wasn't for lack of evidence and it wasn't for lack of a plausible mechanism. So a major factor contributing to the rejection of continental drift was that it was understood to be incompatible with the model of the Earth's crust that was accepted by leading American geoscientists. And I should say that one of the challenges in explaining this episode in history was the quite different reaction of American geologists versus European geologists at this time. So any explanation had to somehow account for that. And so part of the explanation is what I'm about to tell you. So I would say this was one of the major reasons explaining the difference between the American and European reactions to the theory. So to explain this, I need to take a little bit of a detour into early 20th century Earth science. So one of the big questions of early 20th century Earth science was the problem of isostatic compensation. That is to say, in plain language, why do mountains stand up If you think about a great mountain range like the Alps or the Himalayas, there's a huge amount of weight of rock in those mountains. So why don't these mountains just collapse on their own weight? Why doesn't the weight of the rocks crush the rocks at the bottom of the mountain range? And moreover, given that there is this giant mass of rock sitting on the surface of the Earth, you would expect that mass of rock to exert a strong gravitational effect. So if you were a surveyor with a plumb bob standing close to Mount Everest, you'd expect your plumb bob to be deflected in the direction of Everest. But when scientists made those corrections, they didn't work. They found that actually the plumb bob was not deflected. It was as if the mountain wasn't even there. So this was a major problem for Earth scientists to understand, and also a practical problem in cartography. So the answer that scientists developed was the idea of isostatic compensation, that the excess mass on the surface that was visible was compensated by a deficit of mass below. Now, there were two ways that this could be achieved, and so this led to the development of two different models of isostatic compensation. The first one, known as the Airy model, developed by George Biddle Airy in the United Kingdom, was sometimes also referred to the iceberg model. Imagine that the crust is like an iceberg, where what you see on the surface is just the tip of the iceberg, and there's actually this big root beneath it. If the crustal materials were less dense than the mantle materials surrounding them, then this would be a stable situation, like an iceberg at sea, and it would explain why there was no deflection of the plumb bob, because the total amount of mass in any one of these columns would be the same. But some other scientists, particularly John Pratt, pointed out, well, that's true, but the same result could also occur if these columns of rock were different density. So in this model, they're all the same density, but different depths. In this model, the depth is the same, the so-called depth of isostatic compensation, but the density is different. So the lower areas are more dense, like lead. The high mountains are less dense. He uses the mineral pyrite as an example. Mathematically, these two models are equivalent. They both give the same result, the same predictions as to what the gravitational effects on the surface of the Earth would be. So from a geophysical perspective, we could say that the two models were equally consistent with the observed empirical data. Or from a philosophical standpoint, we could say that the choice between them was underdetermined. But as we know, even when philosophers will say that something is underdetermined, scientists do make determinations. They make choices. They don't just throw up their hands and say, oh, it's underdetermined, we can't do anything. And in this case, Europeans chose the Airy model, but Americans chose the Pratt model. Now, why did Americans choose the Pratt model? Well, more precisely, they chose something that became known as the Pratt-Hayford spheroid. In the early 1900s, the American geodesist John Hayford, who was the chief of the geodesy division of the U.S. Coast and Geodetic Survey, used the Pratt model to interpret surface gravity measurements in the United States. So in other words, he's doing cartographic work, trying to make accurate maps of the landscape and the coastlines, and he needs some model to do the gravity reductions, to do the calculations, and so he uses the Pratt model, and in doing so, he produced a new model for the figure of the Earth, that is to say, the shape of the globe as a whole. And this is just his picture kind of showing uniform depth of compensation, and the compensation can occur locally or regionally, depending on the situation. In 1924, the Hayford spheroid was adopted as the international standard for the figure of the Earth by the International Union of Geodesy and Geophysics. Now, this might be hard to imagine if you've grown up in an era where American science is dominant, but this was a huge milestone in American science. It was the first time that any major development or model from American earth science had been adopted as an international standard. And it was something that American scientists were incredibly proud of, so much so that it was actually written up. This is an article from the New York Times about this work, although ironically they show a picture of an iceberg to illustrate it, so it's a messed up picture. It's a completely wrong illustration, but it's celebrating this Hayford spheroid. And this model, then, the Pratt model, came to be known in America as the Pratt-Hayford model. But here's the catch. The Pratt-Hayford model was understood to be incompatible with continental drift. Why? Well, because continental drift required horizontal motions, horizontal forces to propel the continents. And when continents collided, there would be compression, and so it would cause the material to thicken. So just imagine like 2 blocks of clay, you smush them together, and the clay is going to end up thickening both in an upwards and downwards direction, assuming that the area below it is plastic. So if the continents collided, the compressive forces would generate mountains above, but also roots below. In other words, it would generate a picture like the Airy model. So if continental drift were true, then the Airy model was the correct model of compensation. And spoiler alert, today we would actually say that the Airy model was correct in the sense of being a more accurate representation of the structure of the crust, but no one knew that at that time. Hayford's protege and successor at the Coast Survey, this man William Bowie, became one of America's most active and vocal opponents of drift for this reason. And he wrote, this is in a letter to a colleague, if we have the area isostasy, then there must have been horizontal movements forming roots to topographic features. Conversely, if there are no roots, then there can't be horizontal motions. So if you believe that the Pratt model was the correct model, it logically implied that continental drift couldn't happen. And this was why Bowie and many of his colleagues in America rejected the theory. If continental drift occurred, the Pratt model could not be a correct depiction of the structure of the Earth's crust. But Bowie believed it was a correct description, and so he rejected continental drift. Now, this leads to the obvious question, well, why did he believe the Pratt model? But we kind of already know the answer. Because it worked. It was so successful. The Pratt model was the foundation for Hayford's successful model of the figure of the Earth. It was the foundation for this signal scientific achievement. And so Bowie and his American colleagues held by the Pratt model and rejected continental drift. But that invites us to push the question back even further and say, well, why did Hayford adapt the Pratt model in the first place? And here I got really lucky because Hayford answered that question. So in the archives, I was able to find Hayford's reports and writings on this, and he explained, quote, and this is 1909, the assumption of Pratt isostasy was adopted as a working hypothesis because it happens to be that one of the reasonable assumptions which lends itself most readily to computation. In other words, Hayford did what scientists do all the time. He made a simplifying assumption, the assumption of the uniform depth of compensation, in order to make the problem mathematically tractable, in order to make it solvable. Moreover, he had to do this as the problem was otherwise insoluble. So today, this would not be an issue. You'd solve on a computer with some numerical methods, life would be good. But at that time, there was no way to solve this problem without doing something to simplify the mathematics. And Hayford explained that as well. He wrote, very early in the investigation, it was realized that to make the required computations by any method known to have been hitherto used would have been impossible on account of the great expenditure of time and money involved. It was necessary to devise some new method of computation or to modify old methods so as to make these computations feasible. And so those new methods were the assumption of the uniform depth of compensation and, I should have another slide for this, but I didn't in the interest of time, to hire women to do the computations because women were cheaper. Now, William Bowie knew this. This wasn't a secret. It wasn't something that Hayford hid. Hayford was a very honest and open scientist. He explained his methods very carefully, and Bowie understood it. So 20 years later, in 1927, he wrote, to make the theory of isostasy at all feasible, Hayford had to make certain assumptions. These included that the compensation extends to a certain depth, and that this depth is the same for all parts of the crust. While they were necessary to simplify the computations, neither Hayford nor the writer believed them to be strictly true. So in other words, they understood that this was a representation. They weren't stupid people. They weren't naive. They understood that they had done this for mathematical tractability, and yet, in time, Bowie came to act as if he believed it was true. That is to say, as if it were not merely a simplifying assumption, but actually an accurate description of the structure of the Earth. So an idea that was initially accepted for pragmatic reasons became a conviction about the makeup of reality, a conviction that was sustained because it worked. And I think scientists do this all the time. I think many of the things that we believe, that we claim, that we describe as, facts or well-established theories are things that work for us. But if we really asked ourselves, well, if we were honest, we might know that we don't actually know if they're strictly speaking true, or maybe we're not that mindful, and so we're making the assumption that because they work, they're true. So here I'm influenced by the work of Willard Van Orman Quine, who famously argued that we don't judge ideas in isolation. We judge them as wholes. And if accepting an idea X means giving up a well-established idea Y, we tend to cling to Y and forgo X. If things are working for us, we're loath to change them. Now, I think that most times in science, that's probably the right thing to do. If a theory is working well, you'd be kind of silly to throw it out. But the problem is in science is that often we don't know why we accepted the theory in the first place. And especially for you young people, a lot of times your professors don't tell you why that theory was accepted in the first place, often because they don't even know themselves because they never studied any history. But if you go back and look, you often find this pattern that the reason why something was accepted was for practical rather than evidential reasons. Or it could be other things. It could be questions of elegance. There are all kinds of scientific values that can kick in for why scientists accept certain kinds of theories, which then, in the fullness of time, those initial reasons become forgotten. So this is obviously a cautionary tale. It's a tale about not being overly committed to scientific theories that have worked for us, but may, in fact, be underdetermined. There may be other explanations that could also work. So where does this leave us with respect to climate change? And this is where now I'm going to, now that I've taxed your patience for half an hour with a lot of history of science, to show how this then led into what then became my life's work. So in the Sarton lecture, I posed this question. This slide is actually taken from the Sarton lecture. You can see it's kind of pixelated. But where does this leave us with respect to climate change? So in the 2004 lecture, I argued two main points. First, that while many politicians were claiming that there was no consensus on anthropogenic climate change, in fact, there was. There was a scientific consensus, and this contrasted with the continental drift debate, where there was a large argument, where there wasn't a consensus, where there was a very substantial difference between what Americans were saying and what Europeans and others were saying. So in any scientific debate, it's important to understand the extent and the character of the debate, and to distinguish between scientific controversy and political contestation. So I began to argue that climate science, like the debate over tobacco before it, was not scientifically controversial. It was not similar to the continental drift debate, but it was politically contested. Second, I argued that if the evidence for climate change relied entirely on models, then we might have grounds for skepticism. And, in hindsight, if you look at the continental drift debate, right, the mistake I would say that Bowie made was, okay, so he has this model that's working well, but meanwhile, there's all this other evidence from stratigraphy and paleontology that he's ignoring. So obviously, we shouldn't be ignoring evidence, especially if we think it's good evidence. So in climate change, the basis for understanding the climate system is not just global general circulation models. It's historic temperature measurements, it's proxy studies of things like tree rings and coral reefs, it's the evidence of receding glaciers, isotope studies of marine and lake sediments, the well-established theoretical framework that links CO2 as a cause to warming as an effect, and predictions that scientists had made going back to the early 20th century that had now come true. Moreover, the models were in fact being used as I had suggested in 2004 that they should be, primarily to explore what-if scenarios. If carbon dioxide doubles, what is the equilibrium sensitivity of the climate system? But there was a third point that I should have made at the time, so I'm going to make it now. The Hayford spheroid worked for the purposes for which it was intended, even if we would now in hindsight say that it was not literally true. And the same is true of Ptolemaic astronomy. Models can be incorrect in their representations of nature on a large scale, on a meta level, and yet still perform well for their purposes. Now, there's a big intellectual question about why this is so, and I'd love to talk about that if people are interested in that, because I think this is a question that philosophers of science have not nearly done enough work on. I mean, how is it that a model that in hindsight we would say was wrong could in fact still work so well in context? So we know that climate models are simplifications. Any climate scientist would tell you that. We know they're not literal mirrors of the climate system, but we have good evidence that they nonetheless work for many of our purposes. So we can use them as tools even while acknowledging that they're not literal representations of the climate system. Okay, so to return to the issue of consensus. So at that time in 2004, I was particularly concerned to stress this point because, and as I stated at the time, even as the Kyoto Protocol had come into force, the reality or severity of anthropogenic climate change continues to be challenged by opponents of constraints on carbon emissions. One form this challenge takes is to deny the existence of a scientific consensus. That is to say, I was already aware of the fact that there was a political debate taking place in which political opponents of controlling carbon pollution were trying to claim that there was no scientific consensus and use that as an excuse to delay action. And one example of this that I gave at the time, Christine Whitman, who was the head of the Environmental Protection Agency at that time, and generally considered to be a reasonable person, not considered to be a climate change denier, she was quoted in the New York Times in June of 2003 discussing a major report that the EPA had issued on climate change. As the report went through review, there was less consensus on the science and conclusions on climate change. So as if somehow as if the peer review process had failed to come to consensus. And this was the impression that she and other politicians were giving. But I knew that that was not an accurate characterization of climate science. I was a historian who studied scientific debate, and it was clear to me that this wasn't one. It felt different, it smelled different, it looked different. Everything about it felt different. And so in my lecture, I said, there is a clear scientific consensus. Earth is warming, and human activities are at least part of the reason why. Well, today we'd say they are the reason why, but at that time I was being careful. So how could I have said that so confidently in 2004? Well, there were two main reasons. First of all, I had reviewed the consensus statements of major scientific bodies. Already at that time, all of the major scientific societies whose expertise involved earth science, climate change, meteorology, atmospheric physics, had issued consensus statements. For example, the IPCC in 2001 had written, human activities are modifying the concentration of atmospheric constituents that absorb or scatter radiant energy. Most of the observed warming in the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. And that particular sentence was repeated in many other reports, including a major report by the US National Academy of Sciences, where the Bush administration had explicitly asked them, do American scientists agree with the IPCC? And the Academy had said yes. And similar statements had been issued by the American Geophysical Union, the American Meteorological Society, the US National Academy of Sciences, and other groups. Indeed, the American Geophysical Union statement had struck me as being remarkably unequivocal, because as we all know, scientists tend to hedge a lot, have a lot of caveats, a lot of thises and that's and maybes and probablys. But here's what the AGU wrote in 2003, nearly 20 years ago. Human activities are increasingly altering the Earth's climate. It is virtually certain that increasing atmospheric concentrations of carbon dioxide and other greenhouse gases will cause global surface climate to be warmer. Some impacts have already occurred. The unprecedented increases in greenhouse gas concentrations, together with other human influences on the climate, constitute a real basis for concern. Similarly unequivocal was the American Association for the Advancement of Science. The world is warming up. Average temperatures are 0.5 degrees centigrade higher than a century ago. Well, now that's a whole degree. The 9 warmest years this century have all occurred since 1980, and the 1990s were probably the warmest decade of the second millennium. Pollution from greenhouse gases, such as carbon dioxide and methane, is at least partly to blame. In short, there was an expert consensus that humans had changed the chemistry of the Earth's atmosphere by increasing carbon dioxide. The carbon dioxide is a greenhouse gas, that logically we would expect this increase to have an effect of climate, that more effects likely would occur if CO2 continued to rise, and both of these predictions had now already come true. I can skip that. So we had all these statements from scientific societies, but one question that was bothering me a little bit at this time was, well, here's the thing. I have enough sociological training to know that just because the leadership of an organization says something doesn't mean the rank and file agree. My dean has often said things that the faculty don't agree with. Your professors may say things students don't agree with. One study at the time that I read when I was trying to think through this issue showed that large numbers of Catholic priests think priests should be allowed to marry. That number is probably even higher now. So just because the Pope says, and the Pope says don't use birth control, but we know that most American Catholics do. So you cannot assume that because the leadership of an organization says something that it necessarily accurately reflects the views of the rank and file. And so I started thinking about, well, how would we test that in science? So in the case of the Catholic Church, you can do an opinion poll and ask Catholics what they think about birth control or if they use birth control. Or you can ask priests what they think about priests marrying. But how are you going to get at what scientists actually think about climate change? And I thought, well, what scientists think about climate change is in their published peer-reviewed journal articles, right? And the question is whether or not these consensus statements accurately reflect what's in the peer-reviewed literature. And so I decided to test this hypothesis by asking the question, are these consensus statements consistent with the peer-reviewed literature? And so using the Institute for Scientific Information database, this is before Google Scholar, I did a keyword search on the phrase global climate change. I downloaded 928 abstracts that had those keywords, and I asked myself, how many papers in these journals disagree with that statement that I read you a minute ago? Human activities are modifying the concentration of atmospheric constituents that absorb or scatter radiant energy, etc. So the default assumption was that the IPCC did reflect the scientific community, and I was looking for evidence to refute that assumption. And I say that only because you'll see some studies that get different numbers than I did, and it's because they used the opposite default assumption. And the interesting thing is when you use the opposite, so John Cook's famous study, he used the opposite and came up with 97%. That's a number you've probably heard a lot. I came up with 100%, so that I think is good. It tells us the correct answer is between 97 and 100%. Okay, so here's what I got. And this work is now so old that my slides are corrupted, so I had to photograph this out of a later published version of it. But I didn't just divide it into yes and no. What I did was I tried to sort out the papers into what were the papers kind of doing. And what I found was that quite a few of the papers explicitly endorsed that consensus position. Quite a few of the papers dealt with methods, so they didn't really say one or the other. A lot of papers were about climate impacts. That was the single biggest group, was climate impacts. Some were about historical climate change, some dealt with mitigation, but not one refuted the consensus position. So I did it for each year going back to 1993, which was the first year. Wait, why did I choose 1993? I can't even remember now. There was a reason. I think it was I was trying to do 10 years of data. So I did it for every year going back to 1993. And the results showed that this consensus had been established since the mid-1990s, which was consistent with the second IPCC report in 1995, which was the first place where the IPCC had said these things. So this clearly showed that the existing dissent was not scientific, as it could not be found in the scientific literature. Now, I have to say, I really did not consider this part of the talk to be very important. I saw it as a kind of housekeeping detail. I'm trying to be mindful of this issue, this sociological issue about leadership versus rank and files. So I wanted to just make sure I had covered my bases there and had confirmed that these consensus statements were, in fact, consistent with the views of rank and file scientists. So I thought, okay, good. Don't have to worry about that. I get to move on. No. I wanted to go on and focus on the question of my talk. How do we know the consensus is not wrong? How can we justify accepting current science when we know that past scientific conclusions have often been overturned? And especially in climate science, where so much really is at stake. And we are talking about big costs to fix this problem. And just to finish the thought, I wanted to argue, well, we don't know that we're not wrong. We can never say absolutely positively that we're not wrong, but like the theory of continental drift, climate science didn't rely on only models. It relied on a broad consilience of evidence, and this gives us grounds for confidence. And I also wanted to argue that a lot of philosophical work at that time was really focused on scientific theories. Philosophy of science has improved since then. And I wanted to argue that we needed to pay much more attention to evidence, to the amount of evidence, the diversity of evidence, the quality of evidence. And I'm happy to say that quite a few philosophers have, in fact, done this in recent years. Therefore, also, to say that even if climate models were wrong in some respect, like the Ptolemaic model of the universe or the Pratt-Hayford model of the crust, they might still work for their intended purposes. In fact, like the Pratt-Hayford model, they might work better than other models that were more true to nature. Models don't have to be literally true to be useful. They can still generate warranted knowledge. So that's what I wanted to argue. But during the Q&A, all anybody wanted to talk about was the one slide that had the results of the analysis of the scientific literature. All the questions were about that. And we had like 45 minutes of questions and a giant audience, and nobody wanted to talk about what I wanted to talk about. Well, this happens in life, and then you have this decision to make about whether you keep doing what you want to do or whether you kind of respond to your audience. And I decided that I should, well, I didn't just decide. I partly decided, and partly the world decided for me. So what I realized that day and when I went home was that an incredible number of prominent people believed that there was a big scientific debate about climate change, including many scientists, including a lot of people in my audience that day who were professional working scientists. And they believed it because that's what they were hearing, that's what they were reading in the newspaper. So I went home and I wrote this up as an article. One page. The analysis shows that scientists publishing in the peer-reviewed literature agree with the IPCC, the National Academy of Sciences, and the public statements of their professional societies. Politicians, economists, journalists, and others may have the impression of confusion, disagreement, or discord among climate scientists, but that impression is incorrect. So, and then I concluded, many details about climate interactions are not well understood, and there are ample grounds for continued research to provide a better basis for understanding climate dynamics. The question of what to do about climate change is also still open. But there is a scientific consensus on the reality of anthropogenic climate change. Climate scientists have repeatedly tried to make this clear. It is time for the rest of us to listen. Yeah, sadly, I could publish that again today, and probably nobody would remember I had said it 20 years ago. Okay, so I submitted to Science Magazine. I was lucky that they published it. And I also wrote up a kind of more popular version, which I submitted to the Washington Post, who published it as an opinion piece on December 26, 2004. Well, that's a date that some people may remember because that's the same day as the Indian Ocean tsunami hit. And I don't want to at all minimize the damage and suffering that happened in Indonesia and elsewhere. But what happened next felt like a personal tsunami to me. I call it my Alice through the looking glass moment. My life changed kind of almost overnight, and not in a good way. I started getting hate mail. And you have to remember, I mean, now we kind of take it for granted that if you work in certain spaces, you might get hate mail. But this was not something that I had any reason to expect at this time. Threatening phone calls, people calling me up and criticizing me for what I wore, for my makeup or lack thereof. I got one phone call criticizing my choice of shoes. I was defamed on the internet. I was compared to a Stalinist, a communist, a witch. One day I got invited to give a talk at Salem State University. I thought, I am so going to Salem. More seriously, complaints to my university, which led to a formal review of my work. I bought legal insurance. I had more than a few sleepless nights, and I became physically ill with a stress-related autoimmune disease. So this is all really serious stuff. And Professor Gigerenzer has encouraged me to be encouraging to you, to tell you to stand up, don't be afraid, don't be intimidated, take on the big issues, because life is short and we need you to do all these things. And he's 100% right, but I would be being unfair if I weren't honest about what a difficult period this was in my life. It was very, very difficult and scary. And I honestly didn't know if I might lose my job. And there were times when, well, fortunately I have friends in other parts of the world. On more than one occasion, my friends in Australia have called me and said, do you need a job? So that happened when Donald Trump got elected too. I thought, well, it's really nice to know that if things really go south, you have people in the south of the planet who will come to your rescue. So it was a bad time. It wasn't happy. However, here's the thing, and this is why I was a little nervous about giving this talk today, and why I've framed this so much in the context of my intellectual work. Because I don't like to dwell on these things, because I don't want you to be intimidated. I don't want to dwell on the bad parts, because I don't want you to think, oh, holy shit, I'm not going to do that, right? The purpose of harassment is intimidation. So if we allow ourselves to be intimidated, then the harassers win. And so it's really important to say, okay, I get it. I understand what this is. This is an attempt to make me afraid. And therefore, I'm not going to be afraid. I'm not going to let it work. I'm not going to let them win. Plus, and this is the part I really want to emphasize, it is true that there was a bad period. It lasted about 6 months to a year while I was trying to figure out what it was that was happening to me. I mean, I really did not understand why this paper in Science magazine, I mean, it's the most important peer-reviewed scientific journal in America, right? It's not like I published this in, I don't know, USA Today or something. I don't know what the writer, because a scientific article in a scientific journal based on an analysis of peer-reviewed scientific papers doesn't really sound on the face of it like something really inflammatory, right? And I really thought myself of what I was doing as trying to educate scientists and maybe journalists who I thought kind of had the wrong end of the stick. I really was naive enough at that time to think that the journalists were just confused, that they just didn't know. But a lot of good things happened, far more good than bad. And once I began to sort of figure out what was happening, a lot of good things happened. And so I started talking to colleagues about what was going on, and several of them said to me, you need to talk to Ben Santer. So Ben Santer is a really important climate scientist. If you've seen the film version of Merchants of Doubt, he's in it, or if you've read the book begins with his story. He wrote the key part of the second assessment report of the IPCC that said for the first time ever in history that the human effect on the climate system had become, quote, discernible. And for that, he was the victim of a vicious attack in the United States in the pages of the Wall Street Journal and elsewhere. And it nearly derailed his career. It hurt him personally very deeply. He was also multiply investigated. And so I started talking to Ben, and he became a friend. And I learned so much from his experience. And also Mike Mann, who, as you probably have heard of, also has experienced similar things. Stan Glantz, who has stood up against big tobacco. Peter Gleich, important hydrologist, water scientist. And this one, my true hero. Anybody know who this gal is? Someone you should all know. Sharon Eubanks is the lawyer who led the US Department of Justice prosecution against big tobacco and won. A case that everyone thought she was crazy. People said, you'll be wrecking your career, you'll be destroying your career. There's no way this is ever going to work. And it did. And I think we can fairly say that Sharon's work contributed to saving millions of lives through decreasing tobacco use in the United States and elsewhere. So all of these wonderful, amazing people became colleagues and friends. And I began to learn not just from their experience in terms of how I should personally handle what I was facing, but I learned a lot of things. And it was Ben who said to me, we were sitting in his office at the Lawrence Livermore National Laboratory. He's got a totally crap office with, ugly steel bookcases. And he says to me, yeah, I was reading an article one time about the tobacco industry, and it felt eerily familiar. And that was like a little ping in my head. I said, well, is it just familiar, or is there some connection here? And that led to me beginning to dig deeper into this story, to try to figure out who were these people, and what was their motivation, and why were they doing the things they did. And that is what led to my writing the book Merchants of Doubt with my colleague Eric Conway. When we realized that some of the same people who were attacking me, Fred Singer, Fred Seitz, Bill Nierenberg, had worked with the tobacco industry, had attacked the scientists who had shown the harms of tobacco, had attacked Stan Glantz, that these were the same people. It wasn't even just the same strategies, it was actually the same people. And in some cases, the same PR agencies, the same advertising agencies. This was a replay of a strategy that had been developed in the fight over big tobacco. And when I realized that, I thought, oh, well, we have to write a book about this. I mean, then it just became really obvious that the next work that I needed to do. And I feel that I was actually super fortunate. My husband always says the mistake these people made was to attack a historian. Because all these other people were scientists. Well, not Sharon, she's a lawyer, but Stan Glantz, Mike Mann, Ben Sander, they're all scientists. And so when they got attacked, their response was, I just want to do my science. I want to keep doing science. And they worked hard to defend their reputations with their colleagues because they didn't want their colleagues to think they had done something wrong. But as a historian, I was able to ask a different set of questions and to say, who are these people and why are they doing these things? And why is it so important to them to challenge the scientific consensus on climate change? And that led to this book. Sorry, it's cut off. That's bad because I try to be very conscientious about not effacing my co-author. I don't know how this got cut off, but it should say Eric M. Conway right here, a full and equal partner in this journey. And I should say a little something about how Eric and I came to work together. Actually, happened here in Germany. We were at a conference outside of Munich in the town of Poling. I'm probably not pronouncing that. But we were at a meeting of the International Commission on the History of Meteorology. So not exactly like one of your top 10 scientific conferences around the world. Pretty small group, probably about 80 people, and all working on, and Eric was working on a book on the history of atmospheric science, on the history of NASA-funded atmospheric science research. And one of the chapters in his book was about the ozone hole. And at this conference over a beer, I started telling some colleagues about what was going on. And I mentioned the name of this guy, Fred Singer, who was attacking me. And Eric's kind of eyes open up. He goes, well, Naomi, you know that Fred Singer is the same person who attacked Sherry Rowland over the ozone hole. So how many of you know who Sherry Rowland is? Okay, that's bad. You need to all go look up Sherry Rowland. Sherry Rowland won the Nobel Prize in Chemistry for being the person who accurately predicted, along with Mario Molina and Paul Crutzen, that chlorinated fluorocarbons would destroy stratospheric ozone. And he both did the science to make that prediction, but also then became an activist to fight for and help enact the Montreal Protocol. So I consider him to be one of my heroes because he's a great scientist in incredibly important scientific work and also worked to see that policy was made based on that science, policy that has saved lives on this planet, saved a lot of things. So Eric says this to me, and my first reaction was, wait, did you just mention my name in the same sentence as Sherry Rowland? And then my second reaction was, wait, what are you talking about? So Eric had come across all these materials about a very similar kind of attack on the scientists who had done the ozone work. And it was the same people. And then I thought, okay, there's a story here. Something is going on. And I suppose this is the part of what I did that was a bit of a leap of faith. So when we got home, Eric sent me all these documents he had on the ozone story. And I started looking through them, and same people, same strategies, all this familiar stuff. And I called him up. I said, how about, do you want to write a book with me? I mean, I scarcely knew this person. We hardly knew each other. But it was so clear that we had a story, and then he had part of it, I had part of it. And I think he or I, one of us said, well, maybe we should write an article first. So we wrote an article, and we seemed to work well together. And we continued doing work, and then pretty soon we realized acid rain was part of the story, and we started finding a lot more connections to tobacco. Some of my colleagues who'd worked on tobacco, like Robert Proctor, started sending me documents, and it just came together. And as some of you know, it's been a best-selling book. It's been translated into 9 languages, made into a film. And it also propelled me into a role as a public intellectual. So for, I don't know, a long time now, almost 20 years, I guess, a big part of my life has been speaking about these issues, talking about them. I've testified in the US Congress, attended the World Economic Forum many times, done numerous radio and television appearances, got to ski at Davos, you know, hung out with Al Gore. You know, it's been a good run. There's been a lot of good that has come from this, both personally, professionally, and hopefully in terms of my contribution to the world. So yeah, there was about 6 months to a year that was really hard and difficult, but then that's been followed by 20 years of incredibly gratifying and satisfying and rewarding work. Oh, and I just had to throw in this. A couple of years ago, I had the good fortune to be able to take a group of Harvard students to Ladakh, where we did a kind of service learning project installing solar panels in a village in an area of India that has never had electricity anywhere, even though the Indian government will tell you that this region is electrified, but it's not. And just by sheer luck or karma or something, the Dalai Lama was lecturing in the area where we were when we were there. And so we got to meet him. And so there's me and my students with the Dalai Lama. So that was pretty special. Oops, sorry, I think. So, as I've said, I've had the opportunity to make people aware of the character of political opposition to climate change, not just to talk about the science. There are lots of scientists who can do that. But I think the unique thing that a historian or a sociologist or a philosopher can bring to this table is to try to explain the character of the debate, the character of the resistance, and the political and ideological aspects of this problem, something that most scientists are not equipped to do. And to help people understand that the climate debate is not and never has been a debate about climate science. And along the way, I have still continued to try to better understand and explain the nature of scientific knowledge, its strengths and weaknesses, and what we can and cannot expect from science. So if you're interested in that, my recent book, Why Trust Science, is all about that. And I think, oh, and then the final slide, the title of this talk. When all this first started to unfold, I went to speak to my department chair about what was happening, and if I have one piece of advice, it is that if you find yourself getting attacked or being the victim of harassment or intimidation, it's really important to talk to the people around you, your supervisor, your department chair, your family, you know, to get the support that you need to be able to deal with this. So I explained to my department chairman, who was a historian of Mexico, who didn't know anything about climate change or climate science, or probably even science at all. I explained to him what was going on and who these people were, and why they were attacking me, and his response, which I put on my wall and had on my wall for years, surely saving the world is worth a little Saurus. So thank you very much.